Okay, so welcome back. Next, we have Pierre Martin-Dussaud, which is at, now at Penn State University, right, Pierre? And
actually, yes. Yeah.
Good, and he's gonna talk to us about relational locality. Thanks again, Pierre, for stepping up in such a short notice. We really owe you one. And so, do you want to share your screen?
Yes, I can do this. Right.
Perfect. I'm going to tell you when you're at 25, and then, but take it away, yeah, please.
Okay. So thank you all, and thank you for the invitation. I'm very glad to talk about this subject today. So please interrupt me if you have any questions during the talk. It's based on a couple of papers. Here you have the references. And there are also many other papers. I've not written them all, the references. If you want to check them, you can go in the papers and look for the references. So I'm going to talk about relational locality. What is locality in a relational context? So to start with, let's do some history of science and mechanical philosophy. So here you have an image. I don't know if you recognize what this is.
Descartes.
The what?
Descartes.
Yeah, Descartes. Yeah, exactly. So these are the vortices, the ether vortices around the celestial body by Descartes. That's in the mid of the 17th century. And at this time, we believe in mechanical philosophy. And so this is the idea that the world is actually very simple. It is made of simple machines, or it's made of corpuscles that obey the laws of mechanical motion. So we just have space with particles which are moving, and the collision between these particles can explain everything. This idea, which is at the root of the scientific revolution, is not new. If you read Lucretius, for instance, 1 century before Common Era, you will find the same idea. But at the beginning of the scientific revolution, this idea comes back, and it comes back in reaction to the scholastics of the Middle Age. Because the scholasticism was introducing occult qualities whenever something was not clear. Like you want to explain magnetism, you don't know what is magnetism, then you just claim there is some occult quality which attracts some object, and it does not explain much. It's very much like in the theater play by Molière, The Imaginary Invalid, at the same period. There is this quotation, so opium, what is opium? Well, opium makes sleep. And why does it make sleep? Because there is in him a dormitive virtue whose nature is to slumber the senses. Okay, so in order to explain the reason why opium is making people sleep, you just invent a new word, which is dormitive virtue, and this is the occult quality. And so this, of course, does not explain anything. And in reaction to this, the scientific revolution wants to put small wheels everywhere to explain the world. And this, I would say, is the Galilean model of intelligibility. Okay, it's mechanism everywhere. And so when mechanism fails, understanding fails. And Descartes has this model to explain the gravity, why planets are turning around the sun, and that's because there are vortices and dragging. But of course, it does not work, neither. It's not explaining well the phenomena. And so in mechanical philosophy, since the very beginning, has failed in a way. So this other picture is taken from the Principia of Newton. And these are projectiles which are sent from the top of a mountain. So if you send them far away, then it will just go around in an orbit like the moon. And the thing is that the biggest achievement of the scientific revolution does not fulfill the requirement of mechanical philosophy. It's called a twist of fate, like an ironie du sort. And the reason is because if you look at the Newton's law for gravitation, well, you have an action at a distance, meaning that if you change the length between the two bodies, R, instantaneously the force acting on the bodies changes. And so we're introducing some action at a distance which cannot be explained in terms of mechanical philosophy. And this was a big criticism against Newton's theory by Huygens and Leibniz, because they accused Newton of reintroducing some occult qualities with no material substrate. And actually, Newton himself recognizes this fact. This is what he writes in a letter, that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. So Newton himself is not satisfied of his theory, and he recognizes that this action at a distance is problematic. So nowadays, we have another word for mechanical philosophy. It's locality. Okay, it's just the word has changed, but the idea behind it's not so much. Unfortunately, so locality can mean many things depending on the context, but I will retain only two general signification. The first, what we mean by locality is that the interactions between bodies, between fields, whatever, the interactions should happen at the same point. So the same point of a manifold, for instance, if you are in field theory. And the second meaning of locality is a bit different. It's the idea that the causes and the effects of events are no further away than permitted by the velocity of light. Okay, these two notions should distinguish them, even if they are close to one another. And so what's very fortunate for us is that with Einstein's theory of gravitation, we have recovered locality. So we have recovered locality by introducing the gravitational field. So now, in between two bodies that attract to one another, we have a gravitational field that propagates the interaction. And so the two meanings of locality are recovered. The first one, this can be seen if you look at the Einstein-Hilbert action, or the Lagrangian more specifically. The Lagrangian, we have the curvature scalar R, and also the volume elements. But they are acting at the same point of the manifold X. R is a function of X, the scalar curvature. We could have imagined something else. We could have R, if you write R explicitly in terms of the metric, you could imagine that metric at different points of the manifold interact, but this is not the case. Okay, two fields that you multiply together, you multiply them if they are acting at the same point of the manifold. And this is the first meaning of locality, which is recovered by Einstein theory. Then the second meaning of locality is also recovered because you have gravitational waves. And so if you are introducing a perturbation somewhere, like the sun disappears, it will take time before this information reaches you, because you have gravitational wave that will travel at finite speed. And so in a sense, thanks to Einstein, Newton's theory becomes local, and the mechanical philosophy is safe. So this was an introduction talking about gravitation and classical physics to introduce quantum mechanics, because now it might be that with quantum mechanics, the question of non-locality rises again. So there are two reasons for which one could expect quantum mechanics to bear troubles. The first is the collapse of the wave function. So if you take the naive interpretation of what the wave function is and what is a measurement, in an instant, you go from a wave function which is delocalized to a Dirac delta, which is in just one point. And the transition between the two, quantum mechanics tells you nothing about it should go at some speed to respect causality or not. It tells you nothing. For quantum mechanics, the collapse of the wave function is instantaneous. And so, of course, this is there's maybe some difficulty here about the fact that the tail of my wave function, which could be very, very far in space-time, instantly disappears. There is a second reason why we should be careful about locality in quantum mechanics. It's Bell's theorem. Here, it's more subtle. The thing is that if I have two entangled particles which are space-like separated, then the usual story that people say is that if I make a measurement on one of the particle, then it's going to influence the result of your measurement in a space-like separated region. And so this looks like a causal influence in between the two. And we have to be careful about this. So I'm going to talk about these two problems in the rest of my talk. So first, the collapse of the wave function. It's the easiest question, I would say. So I would like to start by saying that there are things that go faster than light. Maybe not physical things, but there are things, and we should be aware of this. So for instance, British sovereignty. Okay, so this example is not mine, it's in a paper of John Bell. So British sovereignty goes faster than light. What do I mean by this? I mean that the day when the Queen will die, sorry about this, but this will happen someday. The day she will die, Prince Charles will become the king instantaneously. However far maybe in the universe, just because at some places the Queen dies, Prince Charles becomes the king. There's nothing that is physical that really needs to travel. It's just a fact. Another example is the shadow. Like the shadow is not really a physical system, right? So if you project the shade of your hand on the moon, for instance, then a very slight motion of your hand will be amplified by the distance to the moon. And so the shadow on the moon could travel at such a high speed on the moon that could go above the speed of light. So that's a bit disturbing, but again, the shadow is not a physical thing. So maybe let's go more, an example which is maybe more technical and maybe easy to grasp in a sense. It's the electric potential in Coulomb gauge. Okay, so that's just Maxwell theory. You solve the equation for the potentials in the Coulomb gauge. And this is the equation that you get. And so you see that on the left-hand side, you have the value of the field at some point. And on the right-hand side, you have an integral over all space-time, over all space, at a fixed instant of time. And so here, on both sides, you have the same t, the same time t. And so if you change the value of rho, so which is the charge, charge distribution, very far from where you're looking at the field, instantaneously, with this equation, it's going to be perceived in the value of the field. So that's okay. But again, the electric potential is not something really physical. Okay, we say the electric field and the magnetic field are physical quantities, but the potential, there's an ambiguity, there's gauge freedom, and so we should not be too much worried about this fact. So that's the first conclusion, is that a physical thing that we are going to call beable, not me, but we will see more precisely what this can mean. But beable should not go faster than light. This is the first requirement. And what these examples show is that the notion of locality is tied to the underlying ontology. I cannot talk about locality if I don't say what is a thing, because otherwise I'm running into many counter examples. So I should be cautious about this. And so what I want, the conclusion that I want to draw from this is that we can add to the list the collapse of the wave function, something that goes faster than light. And this is perfectly okay if we think that the wave function is not a beable, if it's not really a physical thing. But if it's not a physical thing, we have to say what it is, the wave function. And so let's talk about the notion of a beable. So the notion of beable was coined by John Bell in opposition to, or not really opposition, but to complement the notion of observable. He says a theory should not only talk about what is observable, but also what there is really. So he's very a strong realist in a sense. And so he says our fundamental theory should talk about the beables. So beable are all the elements of reality. Of course, depending on the interpretation that you have of quantum mechanics, what you consider as element of reality is going to change. So let's start with classical examples, macroscopic example, let's say, in a classical ontology. What is a thing? So that's really my two pennies contribution to the debate of ontology. And let's be naive for the moment, and I think it's perfectly fine. So in classical physics, we have bodies, systems in more modern terms. And those systems, they have properties. And we can distinguish three kinds of properties. There are the properties which are intrinsic, another word would be essential. These are the properties that really give the identity to the system, that define my system as being a system. They are constant throughout the evolution. So for instance, that can be the mass of the particle. Okay, if in an accelerator of a particle, if I want to, the way they identify which particle has been created is just by looking typically at the trajectory and then identifying what is the mass of the particle. And if you have the mass of the particle, you know what particle it is. In more mathematical terms, one could say it is the Casimir operators which are acting over your Hilbert space in other context. They commute with the other observables. The second kind of properties, I would call them contingent. So those properties, they can have different values, but they are all the same for all the observables or observers. So they are the Dirac observable. Okay, so okay, well, I will give an example. And the last kind of property are relational, and those ones are really perspectival. So they depend on the observer. That can be partial observable. So let's give an example, maybe to make this more concrete. So I take the example of a mug. So a mug, what is intrinsic about a mug? Well, what's intrinsic is the topology of the mug. It should have a genus 1. Otherwise, it's not a mug. If it has genus 0, for instance, this is not a mug. Okay, this is a glass. The reason is because it has not the right topology. It has no handle. It needs a handle to be called a mug. So that's an intrinsic property of a mug. Now, the contingent property of a mug would be the matter of the mug. So here, for instance, you have a mug which is made out of metal, but it's still a mug. Even if the first mug that I've shown you was in clay, both can be called mugs, but the matter of which it is made can be said a contingent property of the mug. But this property does not depend on any outside observers. It's a property of the mug itself. And so the third property is relational property. And so this is, for instance, to know whether the mug is left-handed or right-handed. Okay. Depending on the observers, whether you use your left hand or your right hand, this property will change. The relational properties, in a sense, it's not really a property of the mug, but it's really a property of the relation between the observer and the mug. So that's classical examples, and that's easy to understand. Now, if you go back to the example of British sovereignty and the shadow, in some sense, they can be thought of as relational properties. And we have seen that it was perfectly okay to say that it can go faster than light. So when we say that a beable should not go faster than light, we are really talking about the two first kind of properties, the intrinsic properties and the contingent properties. But for relational properties, it can be fine. I mean, we'll say more precisely what this means. So let's go to quantum. In quantum physics, of course, everything is a bit more tricky. The intuition is more difficult. But in quantum ontology, we have quantum systems. So what is intrinsic about a quantum system is, for instance, the Hilbert space. And it can also be, as I said, the Casimirs. So if you have a group of symmetry which is acting over your Hilbert space, then the invariant, your Hilbert space can be an irreducible representations, which is labeled by some numbers like the mass or the spin. And this can be counted as an intrinsic property of your system. It's defining what your system is about. And then all the other properties in quantum mechanics, they are gathered in the notion of state. And the question, if you want, is to know whether the state is ontic or epistemic. In a sense, in the language that I've just introduced, is to ask whether the state is contingent or relational. Mm-hmm. Do we have to include the observer or not in the game? And relational quantum mechanics claims that the state of a system is relational, it is epistemic. And so a conclusion is that relational quantum mechanics does not violate locality by the collapse of the wave function, because if the wave function is relational, we have seen many examples in which it's perfectly okay to go faster than light. So that was for the collapse of the wave function. Now let's go to the other difficulty that we have seen at the beginning. That's Bell's non-locality. So it's a different kind of locality, and we have to be careful about what we mean by this, especially because John Bell himself never really talked about non-locality, was rather talking about local causality. And he has given a precise definition of what he means by that. It's a formalization of the idea that causes and effects cannot go further away than permitted by the velocity of light. So here you have on the right space-time diagram. Space-time diagram with different space-time regions. And you have A, B, Alice and Bob if you want, and they share an entangled state, singlet. And so John Bell will say that the theory is locally causal if we have this equation. So this equation is an equation between probabilities. So these brackets mean, okay, so on the left-hand side, it's the probability of having the beable A, knowing that I got the beable lambda n and B. And this should be equal to the probability for the beable A, knowing that I got the beable lambda n. So in other words, this says that the beable that I can measure, that I can see, that can have access to in region A, they should only depend on what happened in the past light cone of A. If I introduce some additional information from a space-like region, this should not change my ability to make prediction, my strength, my power to make prediction. It should be exactly the same. So I can erase the B from the conditionals in my probability. This is what locally causal means. So a few remarks. First remark is that the experiments of Aspect, Grangier, and Roger can be understood as this property being false. Meaning, if I have access to space-like separated beables, then I can say more about the beables here and there. Second remark, if we want to interpret this fact, this experimental fact, we need to have a good understanding of what is a beable. So a beable is not, it does not have a very precise definition in the theorem of John Bell. In a sense, it's up to us, up to the interpretation, to say what is a beable. The meaning of non-locality, in the sense of Bell, will depend on what we understand as being a beable or not. Third remark, whatever we call beable, it is not possible to interpret this non-locality as some kind of space-like influence. And the reason is the following, is that if I say that a measurement that I do in B will cause an influence on the measurement that I will do in A, because of special relativity, I can equally well interpret it the other way around. Like, because A and B are space-like separated, there is no sense in putting a preferred time order between the two. And so saying that A influences B or B influences A, these two things, I cannot distinguish it from the physics of special relativity. So no such interpretation.
Yeah, you have 5 minutes, 5-ish minutes.
Yeah, perfect. Yeah. So if we want to understand now the non-locality in relational context, we have to say what are the relational beables. The relational beables, I will say, argue are the relative facts in a past light cone of O. So relative facts, you can say also quantum events, that's fine by me. And so what this means is that if you want to talk about beable, you can only look in your past. And in particular, for an observer who is in A, B is not yet a beable. You have to wait until you reach the common future, O, to be able to express this relation. So from the perspective of an observer in the future, O, this correlation that is observed can be understood as the existence of a common cause, but which is the existence of the correlation and entangled state, but in a context which is indeterministic, and this is where the difficulty of non-locality lies. So just to, what would be the sequence of events, sequence of facts from the perspective of Alice, which would follow this trajectory? Well, in the common past, we have, she knows that there is a correlation between the spins of A and the spin of B. Then in A, she's doing a measurement, and so she knows that SA is up. From this, she can already deduce that SB will be observed down, but that's a deduction. There's nothing that travels faster than light. And after that, when she meets B, then she can check that her prediction was correct. Okay. So that was the definition of Einstein-Podolsky of Rosen of an element of reality. And I said that it is still valid because one can still say that the elements of reality are the relative facts with respect to the observer A, for instance. And so you can predict with certainty the value of a physical quantity. That's perfectly fine. But of course, these relative facts, which are the beable of relational quantum mechanics, they don't travel faster than light either. And they stay with the observer. Because they are states of knowledge, you don't have to imagine that they are things that travel faster than light. Everything is happening locally around A. Now, how do you reconstruct the classical ontology from this very narrow view of reality? Well, you can assign properties to system, as in classical ontology. You can do it independently of the observer, but this is only an approximation, which is only valid locally. If Alice tries to assign properties to B, then we are going to run into kind of non-locality that we don't want to deal with. So if you want to stay to mechanical philosophy, then you have to accept the fact that the states are relational. This is, so the relational perspective on quantum mechanics can be seen as a consequence of the mechanical philosophy. And this is my conclusion in few points that summarizes the point I've made. So first, mechanical philosophy was seriously checked by Newton, but ultimately it was saved by Einstein with the gravitational field. Then quantum has raised trouble again. Third point, there are things that can go faster than light, so should be careful. And in relational quantum mechanics, the collapse of the wave function does not violate locality. Then the interpretation of Bell's non-locality depends on what is counted as beables. So in particular, in relational quantum mechanics, we should look at the relational beables, which are relative facts. And in this case, reality is a sequence of facts gathered by an observer along its world line. And so realism, finally, realism that I call the illusion of reality, is the naive construction, the naive image that you make yourself about reality. Well, this is a reconstruction from your world line, but this is only valid locally in the past light cone. If you try to extend it in space-like regions, then you get into troubles with mechanical philosophy. Okay, that's all.
Thank you so much. Please join me in thanking Pierre. This was great and very provocative. I expect many questions, actually. So as usual, right, oh wait, I have a bunch of people already. So Daniele, and then I'm taking notes. Hanok, I'm taking notes. Daniele, you're up.
Yeah, thanks, Pierre. So I'm fully on board on the whole framework and your conclusions. My question is that the specific nature of the observer doesn't enter at all your argument, and as a result, I would say that your conclusions apply again to all the Neo-Copenhagen type interpretations. Would you agree with that, or is it something that I missed, which is instead specific to relational quantum mechanics in the logic of the argument?
Yeah, so you mean that the observer can be any system? Is it what you mean?
Yeah, so that's certainly specific, but it doesn't seem that necessarily enters the logic of your argument. I know that it's an underlying assumption, but in the logic of the argument, you don't really use this aspect of the story.
Yeah, that's true. No. So yeah, you mean in other interpretations for which the observer can only be some kind of specific system, like a mind or
I would say that so my point is that this way of reconciling locality by accepting the relational or relative nature of facts, which I agree with, it seems to me that in fact it applies to all the other Neo-Copenhagen interpretations. Maybe Richard, who is also in the audience, can confirm that at least it applies also to his.
Yeah, I agree. I fully agree with this. Sometimes it's very difficult to draw lines between the interpretations because one is inspired by another. And so what I call relational quantum mechanics somehow is sometimes a bit fuzzy. It can be many interpretation probably could be called relational. So yeah, I think you're correct about the fact that it's more general than just RQM in the original statement.
Good. Pierre, you have a lot of questions. I'm sorry if I cannot get you through the list, but I mean, feel free to actually write in the chat. I'm sure that Pierre will be happy to respond. So I have Hanok next.
Thanks very much. Thanks very much, Pierre. I like to talk, and I was in agreement with much. I have several questions and remarks, but I'll make only some of them because we have many. One is a historical one. The mechanical world picture of Descartes to Newton did not disagree with immediate action at a distance, immediate in the sense of no time lag. Descartes had his space full of completely rigid bodies. So when the sun presses on its end, you feel the pressure immediately on Earth, namely the speed of light is infinite. So you have, in this sense, you make a small change on the sun without any time lag, you feel it on the Earth. Now, what Newton did is that he did not elaborate any such hypotheses. These mechanical explanations were then called hypotheses, not our sense of hypothesis. That's his hypothesis non-fingo. So the fact that he had action at a distance does not mean his worldview disagrees with the mechanical philosophy, but in his specific case, he doesn't provide an explanation because he doesn't go into hypotheses. That's the change, I think. So it did not mean we reject the mechanical hypothesis and not taken as such by many who try to provide such. Now a question remark about the collapse of the wave function and locality. My impression, I expected something more compact from you. I'll tell you in what sense. If we take the wave function as describing the probabilities that you will have an interaction here or there and so on, there's no physical entity to, that needs to collapse, which is spread around space. It just, you have, when you throw a coin, it's 50-50. When it falls heads up, it's not that the other part collapses in any physical sense. So if the wave function is a mathematical description of the probabilities, then there's nothing that physically collapsed. I'll add something really relevant here. I don't think it's an epistemic thing. It really gives you the probabilities. It's misleading to call it epistemic. Perhaps nobody knows anything. Perhaps it's too complicated for us to calculate. It gives you the objective probabilities. And you have these probabilities, and then you have a specific interaction, and the others become irrelevant. So I thought you can have a more compact explanation of why there's no evaluation of the locality in that case. And I stop here. Thanks.
Yeah, thanks for the two comments. I think, I agree with both of them. After Newton, so Newton was in a sense agnostic about what was the mechanical explanation behind his law, but he still believed indeed that there should be one. And there has been attempts like by Le Sage, I think, and others after that to explain the laws of Newton through mechanical principles until Einstein, and that was the success of it. Yeah, and then for the collapse of the wave function, you're saying I can make the argument shorter. That's true, but yeah, if we think that the wave function is something purely epistemic, then it's obvious. But of course, not everyone agrees with this, and I don't know, maybe some Bohmian interpretation would say that indeed the wave function has something to do with an extension in space-time, and in this case we have to explain, to make sure that we are not troubled with locality and it's more subtle.
They might be in trouble. I mean, the main thing for you is that RQM doesn't have a problem here. If they have a problem, so much the better for RQM.
Yeah.
So we have a follow-up by Richard Healy. Richard.
Thank you. This is a follow-up, first of all, to Daniele's remark. I think in my relational view, I don't want to say that elements of reality are the relative facts. I want to say that quantum states are relational, but such things as the outcomes of our measurements are not relational. So there's more to what I think of as objective reality than observer relative facts. And indeed, I think, in agreement with Hanoch now, probabilities aren't epistemic. Probabilities can be perfectly objective, and there may be a probability that no one knows. And quantum theory gives us lots of such probabilities, in fact, or makes room for lots of unknown probabilities. And indeed, those probabilities would still exist in a universe with no observers, in my view. That's all.
Yeah, I think I disagree with you on both points, but I think, yeah, so you're saying the outcomes are not relational, but the state, the quantum state, is relational. But I think,
and that's why the eigenvalue-eigenstate link does not hold.
Yeah, but I think what is a quantum state? A quantum state is a way to encapsulate some past knowledge that we have about the system, and this past knowledge is obtained by past outcomes. So for me, the quantum states is really just a way to encapsulate past outcomes, and that's why I think if we believe that the quantum state is relational, then the outcomes as well should be relational. Yeah. The second point about probabilities, I don't see really what it means for a probability to be ontic and to be real. I think probabilities are just a convenient way to express statistics about outcomes, and I would not grant them any. But I'm not sure about what you mean either. So for me, probability are epistemic.
But probabilities are epistemically useful, but that doesn't mean to say that they are not real. Something can have an epistemic function without itself being epistemic. As you said, that we assign probabilities, we assign quantum states and therefore probabilities based on what's happened. An agent who happened to be at a particular space-time location would assign those probabilities based on what happened in that agent's past light cone. So the quantum state and therefore the probabilities that it generates, according to the Born rule, will be determined by facts in the past light cone. And those facts I take to be non-relative, and therefore I take the quantum state to be non-relative because it's determined by those facts.
Yes, all right. Yeah, you mean that, yeah, okay. When computing transition amplitude, that Spigner theorem should be the same for, okay, yeah, I see what you're concluding. Yeah, okay, I'm not sure. Okay, I have to think about this. I have to think.
Good, thank you.
We have a lot of questions, so please, if we cannot go over all of them, don't worry. I actually took your name, so we have also the final discussion. You can still ask questions. I'm sure Pierre will stay with us. So Danielle, I'm sorry, I'm going to move to the next question. So we'll move things along. Nick, you're up.
Hi. I apologize if you already mentioned this and I missed it. I'm just wondering if you're saying that if you're hanging on to the state update collapse of the wave function and you're reconciling that with locality by saying that the only facts that are meaningful discussed are relational, and therefore that precludes talking about facts that are space-like separated from yours, that seems to imply a rejection of the eigenstate eigenvalue link, right? Because you update the state vector such that your the state of a distant observer isn't an eigenstate of the observable that you measured in the EPR scenario, for example. And so if you were able to infer from having that eigenstate to the existence of this property, then you would be able to talk about these properties in space-like separated regions. So yeah, does your view entail a rejection of that eigenstate eigenvalue link?
Yeah, my view is that the quantum state is not something that spreads in space-time. It's something about the knowledge, and so if I take a Bayesian view about updating the different state of knowledge, then the collapse of the wave function has nothing to do about locality. It's like British sovereignty. Like when I update my knowledge because I integrate in my set of eigenvalues that the Queen is dead, then I just update my knowledge, and Prince Charles, wherever he may be, just is the king now. Okay, so because about British sovereignty, there's nothing about being spread in space-time. Okay. It's just this. Yeah. I don't know if this really answers the question.
Yeah, that's helpful. Thanks. Yeah.
Okay. Let me see. I lost my list. Oh, here it is. Sorry. Yes, Christian, go ahead.
Annoying, but I guess we have a lot of time for discussion, and we have to start the talk in 2 minutes. So either we skip the break and we take one more question.
Yeah. Wait. So the break was supposed to be at 45, right?
40.
Oh, wait.
No, the break at 45 and the talk at 40.
Okay. So yeah, I mean, it's up to you guys.
The break. Let's take one more question.
Let's get another question. But let me see. Oh, Maximilian, you're up.
Hello. Can you hear me?
Yep.
Great. Okay. Yeah. Thanks for this really nice talk. My question is, so from an Everettian perspective, the way that one would deal with this kind of problem is to say that, okay, well, in order to actually perform the measurement, I have to interact with it somehow, which requires, like, you have kind of locality then baked in somehow, and that this interaction would occur over some time, and this would then, save you from some kind of idea of an instantaneous collapse and any sort of superluminal signaling that might result. But as I see it, it's not entirely incompatible with an RQM perspective. So my question is, what's your opinion on that? Do you think it's necessary to have this kind of British sovereignty kind of argument, or could one circumvent this apparent non-locality by the same way that one does in kind of Everettian interpretation?
Yeah, I think relational quantum mechanics is very close to Everett interpretation. Of course, there are also different varieties of Everettian interpretation. Like it's not initially Everett quantum mechanics was really thinking that the whole world was splitting at each measurement, which is happening anywhere, and was for me too big to swallow. But now there are some refinements about what is Everettian interpretation, and the idea that the splitting between the different branches is happening actually very locally, and slowly it grows bigger and bigger at the speed of light. And I think this is very much very much closer than the relational interpretation. although probably still different. Yeah. So as to explain the non-locality specifically, I should probably, yeah, you should probably tell me more about what is the solution to non-locality and Bell's theorem in everything. Yeah, if you have a reference or something, maybe I would be interested in looking at this. Yeah.
Okay, I'll try and find something. Thanks.
Thanks.
Okay, we had many more questions, but we actually took down your name, Matteo, Richard, Emanuele, so don't worry. Also, Pierre and everyone, both Hippolyte and Aurelian and Anok and Philippe actually had very interesting remarks in the chat if you want to look at it. And join me in thanking Pierre again. This was great. Because we want to leave room for the discussion at the end.